Alright, this is the second video of our discussion. Okay, I'm going to discuss this discussion about implicit derivative. Okay, so I'm going to discuss implicit derivative problem. Question number 5 actually. Following graph is called the asteroid. So asteroid has a formula given as x to the power 2 over 3 plus y to the power 2 over 3 is equal 4. And you have the 2D shape of the asteroid. It's look like this, roughly. Try to draw it. Here you go. This is 8. You can plug, if you plug y equals 0, you can see, cubic root of 8 is 2 times 2 to the power 2 is 4, yeah. So this is 8, this is minus 8, this is also 8, minus 8, okay. You can find those values by, for an example, if you need to find 8 and minus 8, those are x-intercept, plug y equals 0. If you plug x equals 0, you can find the other 2 points, okay? And this is 0. First question asks, find dy over dx. When you find dy over dx, you have to use implicit derivative. So you just differentiate the entire equation with respect to x. The difference is, in the previous cases, most of the cases, when you the y is given, the function is given in terms of x. Here you can't find y explicitly, so that's why we call it implicit derivative. So you take the 2 over 3 down and subtract 1 from the power, so you get minus 1 over 3. That's the derivative of this term with respect to x. And here, when you take the derivative, you just take the derivative of this with respect to y variable, but you are really taking the derivative with respect to x. So you take dy over, you take the derivative of y with respect to x. So always dy over dx attached to it. The derivative of 4 is 0. Okay. So this is pretty kind of easy implicit derivative. You can see the 2 over 3 cancel out if I take it to the other side and divide, and it's really x minus 1 over 3 if you bring it to other side and divide by that. But this is really minus powers or indices, so you can make it positive by switching. That's dy over dx. Okay, it really tells you the tangent of this asteroid when you change x and y. For example, let me see. Okay, I have to have a minus here because I bring it to other side, so that's I miss over there. You can see when x and y both positive, you have some positive over positive and you have minus, so the slope is negative. Any point if you choose here on the first quadrant, the slope of the tangent line to the curve is negative. Here, when you have x negative, y positive, then you get a minus sign when you divide y over x, so it's going to be positive again. Here, both x and y negative, so it will cancel out and you have a negative sign always. It's negative as previous, like first quadrant situation. This is same as the second quadrant situation. It's like a symmetric shape, you can see. Right, part B, find the tangent line. Somebody use a different color. Find the tangent line to the asteroid at this point. Negative, so this is the point. I'm going to write it here, negative 3 root 3, comma 1. Tangent line at that point. So the tangent line at that point would look like this. I know it's a positive slope, but how do you find it? The slope of the tangent line is dy over dx at that point. And plug x negative root through 3 times root 3 y1. So I'm going to plug it here y. Y is just 1, that's nice. 1 over 3 is the same thing. 3, this is tricky. Negative 3 root 3, you need to take the cubic root of that. Cubic root of 3 root 3. Cubic root of minus 1 is minus 1, so it's minus 1, it cancels out. So it's like cubic root of this 3 root 3. So if you take the cubic root of minus 1, it's minus 1. But what is really this? Look at this. If you write 3 as 3 times root 3 times root 3, that's actually 3, right? Root 3 times root 3 is 3. So I have another root 3. So actually it's a product of 3 root 3's. Cubic root means you take one of them, so it's like 1 over root 3. That's the slope. Okay, kind of little algebra you have, because it's like 3 root 3's multiply each other. So that's my part. Okay, still I did not find this equation of the tangent. So equation of the tangent, you need the slope and the point. So y minus y1, which is y coordinate, slope is 1 over root 3, x minus 3 root 3, but minus become plus because this is itself a minus sign. So if you simplify, it gives you x over root 3, root 3 cancel out 3, so if you bring it to other side, it's x over root 3 plus 4. Maybe this will be 4 if you really draw it nicely, it will be 4, because that's your y-intercept. The slope is positive, I know already, it's because of the because of how dy over dx works, okay? At what point the tangent line horizontal and vertical? Tangent line will be horizontal when dy over dx 0, okay? If you look at the dy over dx, you can see, so this is part C, dy over dx is minus y 1 over 3, x 1 over 3. So to get horizontal tangent lines, this is my short abbreviation for horizontal tangent line, you have to set dy over dx 0. So, but if you set it equal to 0, the only situation you can get is y0 situation. y0 at these points, but look at this, when y0, I have a problem in y0, right? So y0 is like these 2 points. Yeah. At 8, there are 2 points I can get, because if you plug y0 here, I can solve for x, which gives me 2 over 3 equals 0, because I plug y equals 0 and 4, sorry. And you can take the square root, which is 1 over 3 is equal to 2. If you square root, it's plus or minus. If you take the cube, it will be plus or minus 8. So there are 2 points that you have horizontal tangent line at 8 and minus 8. So you can say 8 comma 0 minus 8 comma 0. Those are the points that gives you horizontal tangent line to the curve. Vertical tangent lines, to get the vertical tangent lines, you have to have dy over dx undefined. So that means the denominator, which is x to the power 1 over 3, will be 0. The denominator 0 means when x equals 0, you get two y values. We already know it's minus 8 and plus 8. Those are these two situations. You can see at these two situations, I have a vertical tangent line, which is my y-axis actually. Horizontal tangent line is my x-axis, y equals 0. Y equals 0 is my line that gives you horizontal tangent lines. So there are 2 points in that case, tangent lines. So it's like there are two situations. You have vertical tangent lines is this situation. I'm sorry, this should be the other way around. 0, 8, 0, negative 8. My x coordinate is 0 in this case. Right, so that's how you solve that. Okay. Okay, number 6. You can see the question. I'm not going to write down the entire question. It says air is being pumped into a spherical balloon. So what is the volume increase at the rate of 100 cubic centimeter per second? So the volume increase 100 centimeter cube per second. How fast the radius of the balloon increased when the diameter is 50? Okay, when the diameter is 50. So this question, you really need the connection between volume of a sphere with its radius. So the connection is 4 over 3 pi r cube. The volume of the sphere connect with its radius this way. Okay. So rate of change of volume is given dv over dt. So I'm going to differentiate both sides with respect to time because it's a rate of change. So 4 over 3 pi is a constant. I can take out. And r cube I differentiate with respect to r, but I really differentiate with respect to t. So I take it dr over dt. That's the chain rule again. So you differentiate with respect to r first, and you differentiate r with respect to t. So at a certain moment, the volume increased at rate of hundreds. That means dv over dt is 100 cubic centimeter per second. You can use this unit to understand what is the rate. So if cubic centimeter per second means the rate of change of volume, okay, and this is given, and you need to find how the rate of change of radius work in a given moment, which is r equal 50 centimeters. So you just need to plug 100 for dv over dt. This is 4 pi over 3 cancel out. You can cancel out 3 actually. It's easy. 4 pi r square means 50 square, and dr over dt you can find, which is at a given instant the radius is 50, the volume increase at that time 100 cubic centimeter per second, the radius increased 100 over, this is 2500, 2500, yeah, so multiply by 4 is like 10,000 I think, pi, cancel out, it's 1 over 100 times pi. This is centimeter per second. The radius is just 1 unit, like 1 dimension, it's cubic. Volume cubic, the radius is centimeter per second. Okay, I think that's right. Okay, by the way, yeah, 100 is over there. That's right. Okay, so the seventh question, show that a cubic polynomial can have at most 3 real roots or 3 real zeros. This is a well-known result. You know, cubic polynomial can have at most 3 roots, right? It cannot have 4 roots. It either has like maybe one root repeated 3 times, maybe 2 complex root and 1 real root. But you have to show that it's at most 3 real roots it can have. Complex you can have, but sometimes, you know, the maximum number of roots it can have 3, right? So 3 real roots you can have. So you can think, okay, this is how you go. So assume cubic polynomial, a cubic polynomial can have 4 real roots or real roots or zeros. So I want to show that the maximum it can have 3. So, but I assume that 4, and I'm going to get contradiction. That means the maximum it can have 3. I'm sorry. So I assume it has 4 real root, can have at most. Okay, at most. It's a kind of a contradiction method you can use. Okay, I assume it has 4 real roots, but I will get a contradiction. That means it can have only 3 real roots. Okay. This is what you can say. You can think these are the, you know, cubic roots. You can, you know, cubic polynomial. You can assume the basic cubic polynomial look like this. You can put a, b, c, d different values. It's a cubic polynomial, and it has 4 real roots. I assume those are the real roots. Since I use a, b, c, d, can I say x1, x2, x3, x4? Those are the 4 real roots it has. Okay. But look at this. The Rolle's theorem says. So this is the Rolle's theorem says. According to the Rolle's theorem, it says, since these are all roots, I can say xi, you know. So I can find, Rolle's theorem says, since both, for an example, fx1 and fx2, both are zeros, right? So those are roots. So those gives you both are same. I can at least say that they are same. If these are same, it's equal to 0 because they are roots. If they are same, we can find some value in between. How can I say? The value I can say x1 bar inside x1 comma x2. I can find a value in between these 2 roots such that the derivative of the function at that point is 0. It's like I can find a turning point in between these 2. Okay? Right, look at this, you know, like if you assume it has 4 roots, x1, x2, x3, x4. So you can say there are, okay, x1 bar, x2 bar, x3 bar. You can find 3 points in between each of these intervals. Within this interval, you can find one. Within this interval, another one from these 2 intervals, such that I can say the derivative of x bar I 0. I could be 1, 2, 3 because it can be true for each cases. I show you in one case. So that means the derivative will be 0, 3 situations. But look at this. If you take the derivative of this function, it will be a quadratic one. So, but we know the quadratic function has at most 2 real roots. So this condition tells you, okay, there are 3 solutions, x1 bar, x2 bar, x3 bar. There are 3 solutions for the quadratic. It cannot happen. So that gives you a contradiction. You can say our assumption is wrong. You can say quadratic equation has max 2 roots, 2 zeros, 2 real zeros. That means there will be no x4. If there's x4 or like 4 roots, both roots for this function, we have a contradiction. That means only maximum 3 roots can be available. Because if you have 3 roots, you can see, then you can get 2 situations, its derivative becomes 0. It could happen. Okay? Oh, right. So the derivative is quadratic. That means you can have only 2 situations that can turn your graph, cubic graph. So if you have like one situation turning and one situation turning, like these 2 turning situations, you can see here 1, 2, 3. If you have 3 situations, they are turning, it cannot happen 3 turnings in that situation. Okay, right. I think it's clear. You assume first there will be 4 at most zeros, but it could lead to a contradiction. This is a contradiction. Okay, it gives you a contradiction. So contradiction means my assumption is wrong, that it has at most 3 real roots. I can say cubic poly has at most 3 real roots. That's my conclusion. Okay, the kind of a contradiction proof. We use the contradiction method. Number 8. Number 8. It's directly use mean value theorem. Okay, mean value theorem says f of 0 is given if dash of x is always 2, doesn't matter what x, for all x, that's what it's called. For any x, the derivative is 2. So you can apply the mean value theorem like for 2 points. I can say a is maybe what the best number. X, b is 5. F x minus f5. X minus 5. So AB is equal to f dash. X dash of anything in between these 2 points, right? So this you can choose like this is x, this is 5, any point in between these 2. Okay, any point. I can actually see in between these 2. Okay, I choose a to be x, b to be 5. Okay, f of 5 is I'm sorry, f of 0, right? Yeah. So I chose 0 here for my b, okay? I should 0 here. This is my a, b, okay, this is 0, that's okay. 0, x and 0. a, b, okay? F of 0 is 5. Derivative derivative of the function at any point is 2. See, for all x mean, if you plug x, it's 2. X mean like anything, like if you plug derivative at c, it's 2. Derivative at 8, it's 2. Derivative at any point, it's 2. So derivative at 0, whatever, it's 2. So you have x here, so you multiply that with that. So fx is 2x plus 5. That's how you prove that. So they gives us some, one of the data, like one point on the function. This is actually a straight line. So it's kind of giving you the slope and a point. So if you know the slope is 2, because the derivative at any point is 2 for the straight line. And if you plug 0 for your x, what is f of 0? It's 5. It's kind of giving you intercept. It's kind of giving you intercept and slope. But mean value theorem verifies that the function is 2x plus 5.